try some more examples here. This is out of the textbook, or at least an older version of the textbook. Let g of x be the integral from 0 to x of f of t dt, where f is the function whose graph is shown. And I've got some questions to ask. I'll probably let you guys do the sketch for part D, but let's work on the other stuff. At what values of x do the local maximum and minimum values of g occur? Okay, so we're looking for local max and min values for g. And, sorry, some screen rotate issues here, sorry. Remember, g of x is this definite integral from 0 to x of f of t dt. So we need to apply the fundamental theorem to get g prime of x, and g prime of x is just going to be f of x. Now, to find where local max and minimum occur, we need to figure out where g prime is either undefined or 0. So first of all, g prime, which is equal to f, is never undefined on this interval that we're for our graph. Now we need to figure out where g prime, which is equal to f, is equal to 0, and that occurs when x is equal to, let's see, we got 1, 3, 5, 7, and 9. Oh, and 0, almost forgot that. 0, 1, 3, 5, 7, and 9. But now we're looking for where we can have local extrema. So remember, local extrema can't occur at the endpoints, so we can't use 0 and 9. So we're going to eliminate those right away. And let's see, for local extrema, and we're looking at the graph of the derivative of g. We're looking at g prime. All right, so using the first derivative test to find local maxima values, we want to figure out where the derivative changes from positive to negative. Okay, so g has a local max at x equals, well, if I want the derivative to go from positive to negative, that means I'm looking for where this graph is above and then below. Okay, so at 1, the graph goes from being above to below. So there's a local max occurring there, and then there's going to be a local max occurring over here as well at 5. And that's it for local max. And then we would say because g prime, which is equal to f, changes from positive to negative at these values. Now, what about where we have local min? Well, we need to see g prime change from negative to positive. So g has a local min at x equals, all right, well, here, negative to positive at 3, negative to positive at 7, so at 3 and 7, and again, because g prime, which is f, changes from negative to positive at those values. Now for part B, where does g attain its absolute maximum? Now this could occur at the endpoints, okay? So we do have to be careful for that. But let's be clear about one thing. G cannot have an absolute maximum at 3 or 7. So we know we don't, we look for the critical numbers. If we're using the closed interval method, I'd plug in the endpoints, 0 and 9. I'd plug in all the critical numbers. But I don't need to plug in the critical numbers where there are local minimum values, because at a local min, you're never going to have an absolute maximum. You could have an absolute minimum. I'm not looking for that. I'm only looking for the absolute maximum. And so I only need to plug in 1 and 5 to figure out what's going on. Now, I actually don't have a function, so it's going to be hard to figure that out precisely, but I'm going to use some ingenuity to figure this out. So let's just start by noting that g of 0 is the integral from 0 to 0 of f of t dt. And since the upper and lower limits are the same, that's going to be 0. All right. Well, what about g of 1? Well, g of 1 is the integral from 0 to 1 of f of t dt. And if we go use our graphical interpretation of what's going on here, then we're just talking about the area of this shaded region right here. Okay. Now that's a positive number. Okay. So clearly g of 1 is greater than g of 0 because g of 1 is positive, g of 0 is 0. Okay. So I know g of 1 is bigger than g of 0. Well, what about g of 5? Well, again, let's go see what's happening here. Let me switch shading colors. Okay. I thought I switched colors. All right, here we go. So to get to g of 5, I'm going to have to first have area below the curve come up. So all this stuff through here. Okay. Now remember, area below the curve comes out to be negative. So g of 3 is going to be obviously less than g of 1. Okay. But, that's not that exciting for a moment. Now what's happening on the next interval? Between 3 and 5, we're going to add all this area here. Now the question becomes, how does the area that was below the curve in size compared to the area that's above the curve? Now you're going to be doing a little bit of a guesstimate here unless you start cutting out, printing this thing out and cutting out area and then trying to match up to see which one's bigger, which one's smaller. But it looks to me, by my old eyes here, that there's slightly more yellow area here between 3 and 5 than there is this pink area between 1 and 3. So I'm going to say that g of 5 is a little bit larger than g of 1. And then we continue this argument here. If we go into the next region and look over here, then we're going to subtract a bunch of area from that amount. And then we're going to have to go back and add area back in over here to get g of 9. So again, how do these areas compare? Okay. It's really hard to tell. And I'm not looking at the answers in the back of the book to figure out which one that they think is correct. The logic is the most important part here. You have a little bit of area added from 0 to 1. So g of 1 is bigger than g of 0. You have some value subtracted. G of 3 is less than g of 1, but that's not too groundbreaking. G of 5, we add more area back in. I think, according to my eyes, that we're adding in more area than we took away, so that g of 5 is slightly bigger than g of 1. Then we're going to subtract some area between 5 and 7, okay? And then we're going to add some area back. And I think the area that we're adding back between, well, that's awfully close. It's almost symmetrical. It's almost even. So let's just make an assumption here, and if it was a little clearer in the graph, we can make it more definitive. But let's say there's more yellow area than pink area here, and so g of 9 is going to be bigger than g of 5, which is also bigger than g of 1, and so the absolute maximum will occur at g of 9. If you want to make an argument that g of 5 is bigger because that there's more area below the graph between 5 and 7 than there is above the graph between 7 and 9, I would accept that as the answer. You just got to make that argument, and I'd be fine with that. It's hard to tell. I should have chose a graph that was a little clearer, but the concept is the most important thing here. And as long as you understand what I'm saying in in the concept, then the actual precise answer here is something that could be determined later. On what intervals is G concave downward? Well, to figure out when G is concave downward, I need to look at G double prime, and I shouldn't be using a highlighter for that. G double prime of X is going to be F prime of X. And to figure out, I'm sorry, I forgot already. Is it concave downward we need? Yeah, concave downward. That means I need that to be less than 0. And so how do I look at this graph and figure out where F prime is less than 0? Well, if F prime is less than 0, that means F has to be decreasing. So where's F decreasing? Well, F is decreasing between, well, let's use midpoints here just for approximations. 0.5 to 2, and from 4 to 6, and from 8 to 9. Well, those are some bad lines, but so we would say G is CC down on 1/2 to 2, 4 to 6, and 8 to 9. 4 to 6 union with 8 to 9, because G double prime, which is equal to F prime, is less than 0 on these intervals. You know what? It's how do I know? It's good to say that how you know F prime is less than 0, because that has to be true regardless on these intervals. So let's add one more line, one more thing, because we know this because F is decreasing on these intervals. All right, so here's another example to try. So I'm going to add a part C to this. For what values of X is G of X concave upward? So I would like you to pause the video and go ahead and work these parts out, and then come back and see how my solutions worked out. All right, so how would I work this out? So G of 1 would be the definite integral from 0 to 1 of f of t dt. And, well, we're looking at the graph of f. I should have said that earlier, and if you assume that, great, and if you didn't and were confused, I apologize. But G of 1 is just going to be the area bounded by the curve between 0 and 1, and so that's all of this stuff all over here. And so this is just the area of a quarter circle, and the radius of the quarter circle is 1, so it's 1/4 pi times radius squared, or just going to end up being pi over 4. G of 3 is the integral from 0 to 3. Sorry, I don't like the way that my computer is behaving. It's the definite integral from 0 to 3 of f of t dt. And this is going to be, well, we're going to have this semicircle area here that's above, and then we're going to have to subtract from that the area of this triangle that's below. So we have a net signed area situation here. So the area of the semicircle is going to be half pi times the radius squared, minus area of the triangle, which is going to be half. The base of the triangle is 1. The height of the triangle is also 1. So we got half pi minus 1/2, and that's fine. There's nothing really to simplify for that one. Now, where am I going to get g prime of 2 from? Let's rotate this up a little bit. So remember, g prime of x is going to be just f of x. And so g prime of 2 is just f of 2. And on our graph, there's a little bit of a gap over here at 2 in the graph. It's not supposed to be there. For some reason, that couldn't get it to disappear when I was plotting this. But f of 2 is 0. And then I need g double prime of 2. Well, g double prime of 2, g double prime of x, excuse me, is this f prime of x. And so g double prime of 2 is going to be f double prime of 2. And if I go back up here and look at this graph, there at this point here at 2, even though there's a gap there, the gap wasn't intentional, but there is a sharp turn, so this does not exist because of that sharp turn. Because there is a sharp turn. Looks terrible. All right, now we want to find the maximum and minimum values of g on the closed interval 0, 3. So we're going to want to use the closed interval method. And so for the closed interval method, we need to figure out where g prime is either undefined or does not exist. G prime is equal to f of x. Is never undefined. G double prime is undefined someplace, but not g prime. Now g prime, which is f, is equal to 0 when x is equal to 2, as we already saw. And again, over at 3, but 3 is an endpoint, so it's not going to matter separately from us. So now we need to test the endpoints and the critical number. So I need g of 0, I need g of 2, and I need g of 3. The g of 0 is the definite interval from 0 to 0 of f of t dt. Or did I use f of x? It doesn't really matter. It's a dummy variable anyways. So that's going to be 0 because the upper and lower limits are the same. The integral from 0 to 2, we haven't worked that one out. But, or at least, actually we did work that out, but indirectly. That was the area of the semicircle, which we already found out to be as half pi. And then g of 3, we already worked that one out in the earlier example. That's going to be half pi minus a half. So looking at these three numbers here, we can clearly see which one's the max and which one's the min. Okay, half pi minus half is still a positive number, so it's greater than 0, but it's less than half pi. So g of 0, which is 0, is the absolute minimum of g, and g of 2, which is equal to half pi, is the absolute maximum of g. All right, now one last question. The one that I made up at the end there. For what values of g is g of x concave upward? I'm going to work on off to the side of it so I can see the graph. So for concave upward, I need to look at g double prime. And as we've already said, g double prime is going to be equal to f prime. And I want to know where f prime is greater than 0. And f prime is going to be greater than 0 when f is increasing. And so where is f increasing? So if we go back to the graph here, f is increasing from 0 to 1 and from 2.5 to 3. So g is cc up on the interval from 0 to 1 union with 2.5 to 3, because f is increasing, which means that G double prime, which is equal to F prime, is greater than 0 on these intervals. I hope those examples helped. Go study.